Okay, so today is the start of electronics, which the ultimate goal is going to be our robotics project. Um, and we're going to start by, so today we're going to be defining voltage, current, and resistance. Those are going to be the main tools that we're going to use to get electric power to the devices that we need. Um, and in order to study these things, we're going to use an LED to see how it all fits together. You know, that's sort of going to be our visual representation that we have things wired up right. You know, so we'll use an LED to see the electricity. And so first I want to start by talking about electricity in terms of fluid flow. Okay, this is, I think, a really helpful way to kind of visualize what's going on. Because electricity is kind of a weird thing. Like when you take physics 1, you're talking about balls flying through the air and things that you have experience with. Electricity, you can't really experience that same way. So it's helpful to have this sort of way to visualize what's going on. So to visualize electricity, we're going to imagine it as a liquid flowing through pipes. And so the things we're going to think about are, so if you have a pipe, these are the things that relate to each other to create motion of this liquid. You have a pressure on one side. I'll call that P1. And you have a pressure on the other side. And we're measuring the rate that fluid is flowing through some point in the pipe. Okay. And the other thing that determines how fluid flows through this pipe, so you can imagine, like, if you increase the pressure over here, this, and kept this the same, you know, if this pressure was higher than this one, the fluid would go this way. You know, if this pressure is higher than this one, the fluid will flow this way. If they're the same, there's not going to be any flow. And one thing that's interesting about that is it doesn't have anything to do with how high these pressures are. This could be 10 times atmospheric pressure, super high pressure. But if this is the same, there's not going to be any fluid flow. What matters is the difference between those two. Okay. So we're going to think about the flow rate past this point. And we're also going to think about the thickness of the pipe. Okay, so let's say that you have a higher pressure P1 than P2, so the fluid's going to go this way. Okay, what would be the effect? And you know, there would be some amount of flow rate due to that. You could measure it or whatever. What would be the effect on the flow rate if you made this tube thinner? If you constricted it? You have a feel for that?
Yes, I'm guessing it should have like higher like flow rate?
Well, if you make it thinner, if you make the tube thinner, it's going to slow down the flow rate. Think of like if you hooked up, if you somehow could hook up a straw to your hose outside, there would be less water coming out than if you hooked up a hose. Does that make sense?
Yep.
It's that the thinness of that, the smallness of that diameter or whatever, limits the speed of the flow. And you could make it go faster by increasing the pressure or whatever, but that diameter is always going to have an effect on the flow. Okay. So here are some things to remember about this. So if the pressure P1 is greater than P2, the flow goes this way. If P2 is greater than P1, the flow goes the opposite way. And if the diameter of the pipe is reduced, the flow rate is also reduced. And one thing, I mentioned this a second ago, but one thing to notice here is that the flow is not caused by the individual pressures, P1 and P2. It's caused by the difference of those two. So you can think of it as P1 minus P2. And if P2 is bigger, then you get a negative number, and it just means it's going in the other direction. Okay. Okay, so here's the analogy. So keep this in mind as we start talking about these electrical quantities. Here's the electrical analogy. Electric potential is the individual pressures. P1 and P2. It's not really a pressure, it's something else, so the units are different. So the SI units, the international units for electric potential, anybody happen to know what this is? That's a good guess. That's for power. This is volts. Okay. But electrical potential isn't exactly voltage. Okay, so we'll talk about that too. So volts are, the units are given as a capital V. Voltage, this is the thing that really drives electrical flow. Voltage is that difference in pressures. So you can think of this as like P1 minus P2. Okay. the voltage then is the thing that causes the electric flow, causes electricity to flow. Well, if P1 and P2 both have units of volts and you subtract them, then the units you get are still volts. So the SI units are volts again. Makes sense for voltage. And so those electric potentials at various points in your electric circuit, those are things you can measure and whatever. But what is going to matter always is the difference in electric potential from this point to this point. That's the thing that makes electricity flow from one point to the other. And one thing I want you to notice about voltage is voltage is always measured between 2 points in your circuit. So you always have to know what 2 points you're referring to. You can't like look at a circuit and say, what's the voltage? You can only say, okay, I want the voltage between this wire and this spot on this wire. Okay? Because you need to know the electric potentials at both of those two in order to subtract them and figure out what the voltage is. So notice the voltage doesn't, asking what the voltage is doesn't make sense until you choose those 2 points. So voltage is always measured between 2 points in your circuit. And then the last one, so this was electric potential and voltage. And actually, there's 2 more, sorry. But this is maybe the most important one, is current. And current is the rate of flow. So you can think of this as like how much electricity is pouring through this point. And current is always going to flow from the higher electric potential toward the lower electric potential. Okay, so going back to that fluid analogy, that's just saying, the direction of the fluid flow is always going to go from the higher pressure toward the lower pressure. That's the way current works with voltage, okay, or with electric potentials. The SI units for current are amps. It's really short for amperes, which is a guy's name from a long time ago. But everyone just calls them amps. And it's abbreviated with a capital A. And it's important to notice that current has a magnitude and a direction. It kind of makes sense when you think about the fluid flow. But when we're calculating current, we need to know both of those two things. What direction is it going and how many amps is it? Okay. So it has an amplitude and a direction. And if you haven't figured out both of those, then you don't know everything about what's going on yet with the current. And then the last one is resistance. Oh, before I say that, let me say one thing about current. So I said that this is maybe the most important one. Since this is kind of like the amount of electricity flow, and so this is really the thing that powers devices. Okay, this is the thing that you need to make a device work. And so mostly we're going to be relating these things in order to figure out how much current we're sending into a device, making sure it's getting enough current. So we need this to be the right amount for any device. Okay, so if your current is too low, you're trying to say power a motor or something. If your current is too low, the motor isn't going to run, or it's going to run too slowly or whatever. If your current is too high, it's going to start to heat up, and eventually it can damage or break the thing. Okay, so this is the thing we're always keeping our eye on. And then the last one of these is resistance. And you can think of resistance as equivalent to the narrowness of the pipe. Remember that even with the same pressures at the two ends of a pipe, if you reduce the diameter, you get less flow through that pipe. And the equivalent of that in electricity is called resistance. The SI units are called ohms. And the symbol for it is a capital Greek letter omega. So the way it works is for a given voltage, if you increase the resistance, you get reduced current flow. And if you decrease the resistance, you get increased current. Okay, these three main quantities, voltage, current, and resistance, fit together in an equation called Ohm's law. So this relates current, voltage, and resistance. And the equation says the voltage is equal to the current times the resistance. So I'll define these three variable values. So V is the voltage. And we'll talk about the voltage across a device, meaning the electric potential at one side of the device minus the electric potential at the other side of the device. And the device we're going to talk about here is a resistor. I is the current through the device, through the resistor. And R is the resistance of the resistor. Yep.
So if we have a voltage source that's way too high for our whatever thing we're running,
Yeah.
Can we just increase the amount of resistance?
Yeah, exactly.
Okay.
Yep. And that's really how these resistors are going to affect our project. It's just a way to control current. Exactly. Okay, so let me show an example of how this works. So before we start using schematic diagrams and stuff, I'm just going to sort of draw pictures. So let's say that this is a 9-volt battery, and this is the positive terminal and the negative terminal. What that means is, so the battery gives the voltage of the battery. And so you can think of it as the electric potential at this terminal is 9 volts higher than the electric potential at this terminal. Okay, so that's what the plus and minus mean. This is the higher one, this is the lower one. We don't know in any absolute sense what the electric potentials of those are. We just know what the difference is. Okay, but like if we connect a wire around here, electricity is going to want to flow from this, think of the high pressure, around the wire to the low pressure, and that's going to be electric flow. So let's say that instead of this just being a straight wire, let's say we connect this wire to a resistor. And I'm going to indicate resistors with 3 colored bands like that. And then we go to the negative terminal. And let's say that this resistor has a value of 1,000 ohms. Okay, so electricity, a battery doesn't just it wouldn't do any good if a battery allowed the current to just flow through the battery from the positive to the negative. Okay, so those are kept separate inside the battery, and so when you give this electricity a path to get from the high to the low electric potential, electricity will flow this way and come around to the negative. So the direction of the current is going to be like this. What about the value of the current? Well, we can use Ohm's law to calculate that. So if we think of, so we're going to do Ohm's law, and to be careful about this, we need to think about Ohm's law only applies like inside the resistor. So we want to figure out what the voltage is at this side of the resistor. Well, what the electric potential is at this side compared to the electric potential of this side. We have the resistance of the resistor, and what we're going to calculate is the current going through this resistor. Since the 2 sides of that resistor are, each side is directly connected to a terminal of that battery, and there are no other devices or anything in between, you can think of it as like there's an electric potential of +9 over here and 0 over here. You can think of it something like that. And so the voltage is 9. Across the resistor. Voltage also has kind of like a direction. It's called the polarity. So you have to determine which side is higher in electric potential than the other one. You can see here that this +9 side is the positive and the 0 is the negative. So that's the polarity of the resistor. The resistance is 1,000. And so now we can set up Ohm's law, V equals IR. So that says 9 is equal to 1,000 I. Solve for I, and you get 0.009 amps. Or you can also write this as 9 milliamps. Yes?
What is like the correct like abbreviation for like I know they have like you said like this one has like millimeters. Is there like kilo?
Yeah, you can use all those same unit prefixes on amps. For the electronics we're going to do, everything is going to be like, well, we will have some stuff that'll get up over an amp, but for the most part, I guess, speaking kind of loosely, like you can divide up. Part of our electronics is going to be information, transmission of information, so that's going to be coming from the board that we program and information coming into the board we program. And that stuff is going to be very low current. So that's going to be milliamps. And then we'll have other things when we're doing like related to electric power, like if we're powering a motor or something, that can get up into the range of an amp or 2 amps or something sometimes. But you can think of it as like there's the electronics that are just conveying information, and then there's the electrical power that has to do with actual physical motions and things like that. Okay, so in a second here, we're going to use the stuff on the table to sort of see how this works in action. I need to talk about the breadboard before I do that. And the breadboard is this thing. Hopefully you all have one in your box, and it's just a way to wire components together without soldering them or without using clips for everything that can be pretty cumbersome and come off and everything. And so this is how a breadboard works. So a breadboard always has, there are a bunch of holes like that. And a bunch of holes that are shown with black. So there's always one red and one black. And then on the other side, there's a set of holes that are labeled red and another one that's labeled black. And all of the holes along this are connected. So you can think of it as if any wire that you put, any 2 wires that you put into these red holes are connected to each other, but they're not connected to any of the other stuff yet unless we want it to be. And then the holes here are all connected. Same thing with the columns on the other side. And the red and the black, the reason those are there is because it's kind of a pain to, we'll see as we, as you start putting this stuff together, it can be kind of a hassle to take a battery and keep connecting it to places that you want inside the breadboard. So one thing that we're often going to do is take whatever our power source is, plug the positive of our power source into the red. The red always indicates a positive. We'll plug the negative into the negative of our power source into the black. And then from that point on, we don't even have to mess with the battery or the power source. From that point on, we're just going to treat all of these as being our, it's like the red and the black columns are now our power source. And it's just easier to work with. So that's a pretty common thing. And that's how we're going to use those. And then the other connections are, you have groups of 5 holes. And you have a whole list of those, but those horizontal rows are connected, and only the 5 on each side are connected. So these are connected. And these are connected. So if you wanted to use the breadboard to recreate the circuit that we just, yes?
Are the red, like the red, the dot, like the red lines, connected to each other?
Yeah.
Okay. On both sides.
Both sides, yep, that's right. So if you wanted to use a breadboard to recreate the example that we just did that calculation for, you could do it like this. So here's the breadboard. There's the red, the black. I'm only going to draw one side of these, just save a little time, but and then here's the battery. So here's our power source. So we could take the positive of the battery and connect it to the red. We always treat the red like it's positive, but there's really no difference in the wiring of the breadboard. There's no reason you couldn't plug the positive into the black. It's just the red is what people use to signify positive.
Yeah.
Yep.
Will we be using any directional resistors, like things that will break if you plug in the current along?
We'll use some devices that are directional, but not resistors. Okay. But I mean, stuff's gonna break. So if that's what you're asking, is like how nervous do I have to be about this? Like, we'll try to be careful, but stuff breaks, and that's, we don't have anything like valuable for that reason. Yeah.
Well, my mistakes aren't too expensive.
Yeah, exactly. And then I'm going to take the negative and plug it into the black. So that little loop there indicates that we're not connecting it to the red. We're just going over it and connecting to the black. And then I'm going to take an LED. A resistor. And connect it here and here. So there's our resistor. And what we have now is, and I'm not quite done because I don't have yet the resistor hooked up to these power rails. So I'll go, hold on a second. So I'll take I'll go from what's now my positive terminal. Just think of it as like a battery of its own, and we'll connect it to there. And then we'll connect the negative terminal of the battery to there. And so now what we have is we've hooked up the battery to these power rails. And now we can just think of the power rails as the battery. And we go from the positive over to this row, which enters the resistor here. It leaves the resistor here and then goes to the negative down here. Okay. So this is a way we could wire up that circuit that we just calculated. And if we wired this up and measured what was going on, we would see, I mean, if this battery was exactly 9 volts, which they never are, that's something we'll talk about a little later, but if it was exactly 9 volts, we would get a current going through that resistor of exactly 9 milliamps. Yep.
How do you use the bands on the resistors again?
Yeah.
I know that it's like by magnitude, but I don't.
Yeah. So the code is up there on the cabinet. So there are 3 color stripes, and they indicate a 2-digit number. The first 2 are a 2-digit number, and the third one is the power of 10 that you're multiplying it to.
Okay.
So if you wanted like 100, say, actually one of the ones I gave you is 100.
Yeah.
So 100 would be
brown. Yeah, brown.
right.
Black.
It would be, you'd want it to be 10 times 10 to the 1. So it would be brown, black, brown. Okay. So we'll talk about that all more later and stuff. Yes.
I don't know from like which angle is it?
From which end?
Yeah.
Yeah, it doesn't matter with resistors. It's the same. They're the same in either direction. Oh, I gotcha. So it's you can see there's kind of, I guess it's the side that they're closer to is the start. So you know how I always draw it like I draw them all close to one of these 2 terminals. That means that's the side that you would start looking at. So from here it would be brown, black, brown. Okay, well, we could wire this up and it would be working and it would be doing its thing, but it wouldn't be very satisfying because we wouldn't have any way to know what it's doing. So we're going to use an LED in here to light up if we're doing it correctly so we can actually see the electricity flowing. So that's the next thing we're all going to do together. So this is an LED. It stands for light emitting diode. And light emitting, obviously, you know what that means. The diode part means that current can only flow in one direction. So you could apply a voltage in the backwards direction to it, but no current is going to go. You can think of it as like in the backwards direction, it's just a wall. It stops anything. But in the forward direction, it'll let the current flow pretty freely. So a diode is something that only allows current in one direction. And they look like this. You can tell that they have a colored coating. And they, if nobody has messed with them, they have one long terminal and one short terminal. So if you have a long and a short, then that's kind of the end of it. The long is the positive and the short is the negative, which means current flows into this side and current flows out of this side. Sometimes for people's applications, they trim those wires down just to make it fit into a smaller package. And so then you can't use that rule. There's another way you can identify it, and that's that the negative side has a flat edge on it. The wire has a flat edge. So if you can find that, then that's another way to tell which is positive and which is negative. Okay, so if you touch the long side, the positive side, to the positive terminal of a 9-volt battery, and touch this to the negative of a 9-volt battery, this thing would light up. You'd be giving it more current than it wants. Eventually it would break if you kept it on there. But it would work. If you flipped it and put this on the positive of the battery and this on the negative, you wouldn't see any light because that would be trying to make current flow in the wrong direction. Okay. Okay, so what we're going to do, let me go get we'll use a resistor to supply the correct current to the LED. That correct current is about 20 milliamps, although there's quite a bit of wiggle room in the operation. And so we're going to use a 330 ohm resistor, just because that's one that we have in our kits here. So 330 ohms should be, so we want 33 times 10 to the 1. So it should be orange, orange, black. Okay, so look in here and see if you can find one of the, you have several of these resistors that are orange, orange. Oh, I'm sorry, orange, orange, brown, not orange, orange, black. By the way, if you have one that has 4 color bands, and the fourth one is gold, silver, maybe just gold and silver. Those just tell you how precise the resistance is. So these aren't exactly 330. They're somewhere in the ballpark of 330. And like that last band that's like a metallic color just tells you how close you can expect it to be to 330. So depending on how precise your application is. Obviously, it costs a little more to get more precise resistors. Okay, so let me just describe how you want to do this actually, and then you can wire it up and we'll hopefully get this working. So we're going to have our 9-volt battery, positive and negative. And then here's our breadboard. And we're going to connect the battery's positive to the positive power rail and the negative to the negative power rail. So now both of those two rails are powered and we can do the rest of everything off of those. And so now I'm going to go from the positive rail to one of these. And I'm going to go to the 330 ohm resistor. And then I'm going to go from the resistor to the LED. And then I'm going to go from the row that has the negative terminal of the LED to the negative rail. And so the way this works is we go from the positive rail to one side of the resistor, out the other side of the resistor to the positive side of the LED, out the negative side of the LED to the negative rail. Okay.
Does that LED itself have resistance?
That's a good question. It does have a little, but we're going to pretend like it doesn't for now. If you had to draw out what's happening like this all the time to indicate an electric circuit, it would just get to be pretty cumbersome. So people use schematic symbols to represent this stuff. So here are the schematic symbols that for the devices that we've seen so far. The first one is a battery. And it looks like this with a long line and a short line. Sometimes you'll see multiple long and short lines. So a battery is really, we call everything a battery, but really a battery is a collection of cells. And that's why people sometimes you'll see them like this instead, like that indicates multiple cells. But this one works fine for our purposes. And the long line always is the positive polarity and the short line is the negative. The second one is a resistor. And that is like 3 jagged peaks like this. And there's no preferred direction for a resistor. One thing that we're going to use a lot once we start programming things is instead of using a battery, we'll just use a voltage source. And so that will be just like an open circle with a wire coming out of it, and it'll have a value like +5 is going to be a common one. Well, so that kind of suggests that the electric potential of this point is +5. But remember, that doesn't do any good in telling you how electricity is going to flow until you know what the other side is. And so often this will be connected to a ground. And a ground is, we're just going to always treat that as 0 electric potential. And that's indicated as 3 lines like this and sort of like a Christmas tree thing. So there's a ground. And you can use a voltage source and a ground exactly the same way that you use a battery. It doesn't look like a circuit, but that's still just current flowing from one electric potential to the other the same way it does with a battery. And then the last thing we've talked about is an LED. So a diode generally looks like this. So this is a voltage source. And I think this is pretty descriptive of what's going on. It allows current to flow this way, but if you try to have current flow this way, it hits that wall and can't go. So that is a diode, and to indicate that it's a light emitting diode, you just have two little arrows coming out of it representing the light. So let's use these schematic symbols to indicate what we have going on here. So in the example above, I'm going to put the battery down at the bottom. And then we have the positive of the battery going to 300. No, I don't want that. A 330 ohm resistor. And then it's going to an LED. And then it's going back to the battery. And this was 9 volts. So obviously, like, that's a lot easier to sketch out the electronics that you want than drawing the breadboard, drawing the battery, all that stuff. So that's the idea of those schematic diagrams. Anybody have any questions about that? So let's do one simple thing. Go back to this example and draw a schematic diagram of that circuit. Okay. So this is like our first example. But done as a schematic instead of like a drawing. And you can put this stuff anywhere. I guess I'll put it in a different orientation. Like we could do it as the battery over here. The resistor here. This was 1,000 ohms. This was 9 volts. Okay. There is something else that's going to be, so we're going to use resistors like you asked about before. We're going to use resistors to control the amount of current that a device gets. So if we have a power source that would be producing too much current for a device, we'll use a resistor to cut that down into the range that we want. There's some other tools with resistors that are going to be important for that. And so I want to talk about resistors in series and parallel. So first, we'll do series. And you can think of anything in series as like the electricity goes through one of them first and then goes through the second one. It doesn't have any options. Any electricity that goes through one has to go through the other one. So this is when the electricity first goes through one and then the other. So an example of this would be, so let's say we have the battery, and it connects to a resistor, and then a wire connects that to another resistor, and then to the negative terminal of the battery. So the key thing is there, any electricity that goes through one, it doesn't have any other options. It has to go through the other one. That's the key thing about series resistors. As a schematic, it would look like this. And when you have a setup like this, the voltage is divided between the two resistors. And so in order to calculate the current that goes through these, so to use Ohm's law, first, like imagine that these two are just a single resistor. So imagine what's in red here as like a single resistor. Same thing here. So imagine that everything inside the dotted line is a single resistor. And I'm going to call that REQ for the equivalent resistance. Okay. Then the equivalent resistance for things that are in series is just the sum of the two that are in series. So like if this was R1 and R2, and so let me do an example of how you would calculate the currents and voltages for a pair of resistors in series. Okay, so let's say that we have a battery that's connected to a 500 ohm resistor, and then it's connected to a 200 ohm resistor. And let's say that this is 5 volts. And let's say, so we want to calculate the voltage and current for each of these resistors. Okay, well, I'm first going to lump them together. So I'm first going to say, okay, this is a single R equivalent. So R equivalent is equal to 500 plus 200. Okay. And I can redraw this circuit like this. And now I can use Ohm's law. So Ohm's law says the voltage 5 is equal to 700 I. And so I is equal to about 0.007 amps, or about 7 milliamps. What about the directions? This is the positive side. This is the negative side. The polarity of the voltage, you can think of like that positive just slides around the wire over here. The negative slides around over here. The current always flows from the positive to the negative, so the current through there is like this. Yes?
Do we always go to like the first digit or?
No. I don't have a calculator on me, but it's a little over 7.
Oh, okay. So like 7 digits? Or like
No. I mean, I don't know. I don't have a rule about how much to round it to or anything.
Okay.
I just rounded it to 1 there. Okay, but that doesn't give us the voltage and current at the individual ones. And so now we're going to use this fact. For resistors in series, for anything for any elements in series, the currents are the same. So now that we've figured out the current through each one of those, through that combined equivalent resistor, now we can use that current to calculate the voltage for the individual ones. Okay, so now I'm going to expand it back to the original. We have 5 volts. This one was 500 ohms. This one was 200 ohms. We know that the current here is 7 milliamps. The current here is 7 milliamps. And now I can use Ohm's law for each to calculate the voltage. So Ohm's law for each. We have that the voltage for the 500 is equal to the resistance times 7 milliamps is 0.007 in SI units. And so that is about 3.5 volts. And then for the other one, the voltage for the 200 is equal to 200 times 0.007. And that's equal to, well, there's a lot of round off because, like you pointed out, I rounded off a lot here, but, let's say that's 1.5. So they add up to a total of 5 volts. But this is how you figure out what the voltage is and the current in each of those individual ones.
So if you take the voltage measurement in between, like, say, at the start of the 500 and the end of the 500, you would find that the voltage.
That's right. Yep, exactly. Any questions about that? Let me give you a problem like that to do just to kind of solidify this. So let's say we have a 9-volt battery connected to a 1,000 ohm resistor connected to a 10,000 ohm resistor. So what we want to do is find the voltage with the polarity. So that's which side is positive and which side is negative. And the current with direction for each resistor. Spelled that wrong. Okay, so feel free to talk to each other as you do it, ask me questions as you do it, but I just want you to get the experience of doing one of these before you leave class here. An equivalent resistor so this is 9 volts. This is our equivalent. We know the positive is here and the negative is here. And Ohm's law says uh, 9 is equal to, I didn't. So the equivalent resistance is the sum of those two, which is 1,000 times 10,000 plus 10,000. So 11,000. So 9 is equal to 11,000 times the current. Can someone tell me what you got for that? 8.2 times 10 to the minus 4 amps. And so now we know that that's the current going through each individual resistor, and it's going this way. So now I'm going to expand it. And we know that there's a current here of 8.2 times 10 to the minus 4, and a current going this way of 8.2 times 10 to the minus 4. And then we can use Ohm's law. So that first one is on the left was 1,000. So the voltage in the 1,000 is equal to 1,000 times 8.2 times 10 to the minus 4, which is 0.82. Is that right? 0.82 volts. And then we'll go to the second one. So the voltage in the 10,000 is equal to the resistance of the 10,000, times 8.2 times 10 to the minus 4. And that is about 8.2 volts. And you can see that those two voltages add up to our total of 9. It might be off a touch, but that's just round off error. And so we have the polarity of our voltage in this one is like this. And that one is 0.82 volts. And the polarity of this one is this way. And that is 8.2 volts. How did I know the polarity? How did I know what was positive and what was negative for the voltage on those two?
The battery terminals.
That's true. Yeah, that's true. The way I was thinking of it is, remember that with resistors, the current is always going from the positive towards the negative. So if we know the direction of the current, we automatically know the polarity of the voltage. Okay. Okay. Anybody have any questions about that? So I'll give you an assignment with some of this stuff. Yeah, in the next 2 days, get me your STL files and I'll start printing those out. I won't be able to get everyone's printed by next Tuesday, about half and half, half will be the next week. But we'll get those done and then we'll finish up that project as we're working on this. And anybody who wants to talk to me about the projects or whatever, we have a little over 10 minutes to talk about it. Anyone else, you're free to go, stay, eat ice cream, party.